Okay, there's a special case that we want to take a look at. I just spoke about creating a uniform field, and in practice, there's a specific situation that comes up a lot in technical applications where you have one disk that is positively charged, so we'll call this plus Q. And again, this is an edge-on view of a disk. And another disk that is same dimensions, and it's parallel to it, right next to it, but it has the opposite charge. So this is negatively charged. And there's a name for this device. Anybody know it? This is a capacitor. Okay, a capacitor is the simplest capacitor is just two metal plates side by side, and then you connect them, as we'll see later in the semester how you can actually, the mechanism behind charging a capacitor. But basically, if you connect it to a battery, you can drive current onto the capacitor, and charge builds up on either side. So you have what's called a parallel plate capacitor, specifically. Okay. Two disks, opposite, same magnitude of charge on each side, but oppositely signed charges. And so we look at the electric field at various locations here. If we want to look inside the disk, say at an observation location in the gap in between them, the electric field due to the positively charged disk is pointing what way? Pointing that way, right? So that's E of the positive charged disk. The electric field of the negatively charged disk is pointing the same direction, right? Because it's pointing towards the negative. If this distance, we'll call this distance S, which is just the gap in between the two plates. If this distance S is small compared to the radius of the disk, we're not too far away from either plate, how do the magnitudes compare? They should be equal, right? They should be equal because we should be able to use, if we're very close to the disk, we should be able to use this formula as our approximation. Electric field of disk, magnitude of the electric field of a disk is Q divided by the area over 2 epsilon 0. There's no dependence on the distance, okay? So it doesn't matter where we are inside this this capacitor, as long as we're fairly near the center part. Again, if you get toward the edge, the approximation breaks down. But if we're here, or if we're here, or if we're here, or if we're here, the magnitude of the electric field of the positive plate should be uniform. The magnitude of the electric field of the negative plate should be uniform. And so when we add those two together, we know they're in the same direction, so we can say that the net electric field inside the gap would be equal to, in fact, let's write it as a vector. We're going to have Q over A over 2 epsilon naught, 0, 0 for the positively charged plate. And we're going to have Q over A over 2 epsilon naught, 0, 0 for the negatively charged plate. You say, well, what happened to the sign here? It isn't one positively charged, it isn't one negatively charged. Well, you got to be a little bit careful because, again, we're talking about a magnitude here. So that really is a magnitude. And so, as usual, I'm just looking at the physical situation to figure out what the direction of this vector should be. So the magnitude of the field is the same for both, but it's pointing in the positive x direction for E positive, and it's pointing in the positive x direction for the field of the negatively charged plate as well. So when I add those two together, I get Q over A over epsilon 0. So that's another useful result. Inside a parallel plate capacitor, the magnitude of the electric field is just the magnitude of the charge on one plate divided by the area of one plate divided by the constant. Okay, so it's important here to realize this Q is the charge of one plate. The total charge of the capacitor is what? If I add those two charges together, I'd get 2Q. One's positive, one's negative. So the net charge is actually 0, right? So there's no net charge on the capacitor, so it's just a separation of charge. So the Q here is not the net charge, it's the charge of one plate. Okay. Okay. So a capacitor is very useful. Well, it has a number of uses, and we'll see those as we go through the semester. It's useful technologically as for storing charge and storing energy, which can be used later on. But it's also useful for creating situations where we have a uniform electric field. Okay, because everywhere, almost everywhere, inside this gap, provided it's a small gap compared to the radius of the plates, we get an effectively uniform electric field. Okay, how close to the edge? Depends on how good of an approximation you want. Okay, I mean technically, even you move even a smallest away from the center, and this, is not strictly speaking true anymore, right? So it depends. I can't really give a stronger answer than that. For our purposes, we're often going to be looking at situations where we just want to get the basic idea, and so we can often make this approximation. Okay. Yes. Well, what's inside this gap? What's here? What's at this location? Nothing. Yeah, there's nothing here. Okay, so where is the charge? The charge is on the plates. Okay, the charge is on the plates. Well, the question we're asking is, what is the electric field made by those charge distributions at locations inside the gap? Okay. Now, maybe I didn't answer your question, so ask it again. Oh, inside the capacitor itself, as in like here, like inside. Oh, okay. So what I did was, all right. So I'm applying superposition. I have I have a positively charged disk and a negatively charged disk, and I already worked out what the field is due to a single disk when I'm close to the disk. Okay. So I've got an observation location in here that is close to disk number 1. So let's write it out maybe in stages. I have the net field. The net field would have to be the electric field due to disk number 1 plus the electric field due to disk number 2. Or I'll write it this way, the positively charged disk and the negatively charged disk, right? We're just applying superposition. So I say, okay, what's the electric field due to that positively charged disk? Well, I know how to deal with that. Superposition says I ignore the presence of the negatively charged disk. Just think about the positively charged disk. I know its direction is in the positive x direction, and I know its magnitude is q over a over 2 epsilon 0. Okay? So I have a vector then that is q over a over 2 epsilon 0 in the positive x direction. All right? I do the same for the negatively charged disk. If I ignore the positively charged disk and focus on what's the field due to the negatively charged disk, well, it's pointing in that direction, pointing towards the negative charge, and it's got the same magnitude because it's got the same magnitude of charge, it's got the same area, and there's no distance dependence here. If we're close enough to that disk, that's all that matters. Okay, so I know then that it's the same formula. I have another factor of q over a over 2 epsilon 0, and then 0 in the y and z directions. Add these two together, and I'm just going to get, if I add 1/2 of something plus 1/2 of something, I can just get this back, right? So all I'm doing is adding two fields together. Okay. Okay. Questions? What about at a different location? Let's, in fact, ask a question about this. So we know the electric field inside the capacitor, and we're not showing the whole disks here, but you get the idea. One's positive, one's negative. Here's E inside. Here's a little location, this little green X here is outside of the gap. Okay, so it's outside of the negatively charged plate here. Which arrow best represents the electric field at that little x? Think about it. Talk to your neighbor. Okay, so biggest answer is 4, which is kind of pointing toward the negative plate, right? And that's probably a good expectation, because if we are at a location here, we are looking at, again, the superposition of two electric fields. The electric field due to the positive charge is pointing in which direction? That way. Electric field due to the negatively charged plate is pointing that way. And which one's bigger? Field due to the negative, right? Now you might say, well, how many people actually went for 3? Not many. Okay, 4% said 3. Didn't we just get done saying that the electric field is uniform? Well, we're starting to get farther and farther away, right? So that field being uniform approximation might not be a very good one when we start to get far away, particularly farther away from this positively charged plate. So we might have to go back to thinking about looking at the electric field of a disk using maybe the formula Q over A over 2 epsilon 0 times 1 minus Z over R. So we end up with a electric field that's going to be a net electric field pointing that direction when we do the superposition. And let's see if we can work out what the magnitude is. Same idea. The net electric field is going to be the electric field due to the positively charged plate plus the electric field due to the negatively charged plate. And I'm just going to look at the component, the x component. And, okay, they're calling this z, but don't get confused by that. The z distance is just along the x direction in this particular case, so don't worry about that so much. Okay, so the x component would be, we have the field due to the positively charged plate is going to be pointing in the positive x direction. So that would be positive q over A over 2 epsilon 0 times 1 minus the distance from this point to this point. Well, what do we want to call that? Let's see. This distance is S. Let's see. Yeah, let's just call that distance Z. All right, so let's call that distance Z. Even though it's along the x direction, it's okay. So this will be 1 minus Z over R. And then we have the electric field due to the negatively charged plate. So we have the field due to the negative charge is pointing in the negative x direction, right? So it's going to have a negative x component. The q here, I'm just saying, is a positive number, so this is q and this is negative q. Q over A over 2 epsilon 0. I have 1 minus. Now, what's this distance? What is the distance from this plate to this observation location? If this is S and this is Z, then this distance is what? Z minus S, right? Okay, so we have 1 minus Z minus S over R. And if you work this out, let's see, we have, what are we going to get? We're going to get some things canceling out. The Q over A over 2 epsilon naught minus Q over A over 2 epsilon naught. That's so essentially that factor of 1 and minus that factor of 1. We have minus Z over R Q over A over 2 epsilon 0. We have, if we bring the negative sign inside, we have a plus Z over R Q over A over 2 epsilon 0. And we end up with a minus S over R Q over A over 2 epsilon 0 when we work out all the algebra. So a lot of things cancel out here. That cancels out. That cancels out. We end up with the x component. I'm just going to look at the magnitude here. The magnitude of the field of a capacitor outside the gap on the center axis. Q over A over 2 epsilon 0 times S over R. This depends on the geometry, or depends on the area. It also depends on the size of the gap. The bigger that gap, the bigger that field is going to be, because you have a more of a difference between these two fields, and you get less cancellation. Okay. If I squeeze these two plates together, that S gets smaller and smaller. These fields get closer to looking more identical to each other, and this gets closer and closer to 0. This thing is called the fringe field of a capacitor. So it's the field outside of that gap. It just has a special name, and we'll be using that occasionally through the semester as well.